So third time is the charm for trying to record this. I'm going to start with page 141, the question 10 that was for homework. So when we are looking at this, in this particular question, you have two equations. You have KMnO4, you have iodine, and you have sodium thiosulfate. And I really would recommend that when you put together your beginning table that you include the iodine in there. It'll make things really clear for you. So the information from the question looks like this. And the ratio in our first equation was 2MnO4 minus to 5I2. And then in our second equation, we have to multiply everything across the line by 5. So that gives us 5 iodines and therefore 10 thiosulfates. In this particular question, they are going to ask about concentration of KMnO4, concentration of iodine, and concentration of sodium thiosulfate. So putting your table like this will help you in the long run. So our way in is over here, the 0.022 molar, and the end of our question asks us to identify the concentration of sodium thiosulfate, and this is our question mark, our final place. So we start at the beginning as we always do. So that 0.022 big M is the equivalent of 0.022 moles per 1,000 centimeter cubed. We turn that into moles per 1 centimeter cubed, and we multiply by the titer volume to find the moles at the end point. So that's why this is highlighted in pink. The first question that is asked, how many moles are present in 25 centimeter cubed portions of the 0.022 moles per liter potassium permanganate? So we have now done this. It then asked how many moles of iodine were liberated in the reaction, and this is now where we're using the ratio. So the ratio is 2:5, so we divide our 5.5 by 10 to the minus 4 by 2 and multiply it by 5, and that's now giving us our moles of iodine at our end point. So that is our second marking point. The next question is asking you to identify the concentration of sodium thiosulfate in moles per liter. So now we've worked out a ratio of 2:5, and I'm going to finish it up here by working out what 5:10 is to find moles of sodium thiosulfate at our end point. So with the ratio being 5:10, we divide the 1.375 by 10 to the minus 3 divided by 5, multiply it by 10, and that's now giving us 2.75 by 10 to the minus 3 moles of sodium thiosulfate at our end point. So in terms of the W we are at this point here. We've used our ratio, we're on the right hand side, and we're going to turn the concentration into moles per 1,000. So we divide it by the titer volume and we multiply it by 1,000. So that's giving us 0.1225 big M of sodium thiosulfate. Now it wants us then to turn it into grams per litre. In the SEC questions, the concentrate or the substances they want you to put into grams per litre is always going to be written in bold, but we only have it in words, sodium thiosulfate. So that's why over here we have Na2S2O3, and that gives us a molar mass of 158. So we use our mass triangle, we multiply 0.1225 by 158, it gives us 19.36 grams per litre of Na2S2O3. And the very end part of it asks us in part C, grams per litre of crystalline Na2S2O3.5H2O. So it's the whole thing now. So we're going to add in 5 waters, that's 5 by 18, onto our 158 up here, and we now have 248 grams per litre. So we again go back, we multiply 0.1225 M by 248, and that gives us our final answer, 30.38 grams per litres of crystalline sodium thiosulfate. So you have to be reading in the question. You're not looking at equations, you are looking for something that is in bold in your equation, and that is the substance that you are going to be using to calculate molar mass, unless they specifically ask for ions, which is unlikely. Okay, so we are looking at now page 142, and this is the final redox titration that we're going to look at in this academic year. So you have to figure out what's the difference when we did iodine thiosulfate and bleach thiosulfate. So something a little bit about household bleach. So the chlorine that it contains is in the form of what's called sodium hypochlorite. So this is our formula, NaClO, and you should be really good at this point now at being able to work out oxidation states. So oxygen is -2. There's no other one of the weird rules applies in this instance. The sodium is always +1 because it's a group 1 metal. It has to mean in this case that the chlorine is a +1 oxidation state. Okay. So I'm not going to ask you to do the balancing of the equation. You should be able to do it by now. So this is our titration reaction, and if we just look at it in terms of oxidation, so we've said here this is +1, our iodine here is -1, our chloride is -1, and our iodine here is 0. So my chlorine is going from +1 to -1, that is a decrease in oxidation number, that is reduction. My iodide is going from -1 to 0, that is an increase in oxidation number, that is oxidation. It means if this is the is reduced over here, then this is my oxidizing agent, and you are writing it in full for the SEC should they ask it for you. When we do this particular titration, we have to dilute our bleach with distilled water, and we do that for mainly because of the quantity of reagents that we would end up having to use. We'd be filling our burette again and again and again. We also use distilled water in this titration because we've seen that if there's any chlorine in the water that can act as an oxidizing agent, it's going to affect our titer, the accuracy of our titer, and also it makes the reaction cloudy, and we're looking for a colorless endpoint, and that's going to be really, really hard to determine. So in this particular reaction, it's the exact same as the iodine thiosulfate. We have to liberate iodine in our flask, and what we're going to do is we're going to dilute the bleach. It's going to react with the Ki in our flask, and it's going to liberate iodine for us, and then we titrate that iodine against a standard thiosulfate solution, and then we just work back to work out our concentration of sodium hypochlorite. The excess Ki blurb applies here, so that is the idea that the fact that the bleach and your Ki, when they react, they will form the triiodide ions, the I3-, and remember we said about this, it works exactly the same as I2, and it is more soluble obviously in water than I2 would be. We have the excess Ki in there to keep the iodine in solution, should it be asked as a question. So the only difference between this titration and the other iodine thiosulfate titration is how we're making the iodine. So in the past, this time around we're using diluted bleach, whereas before the other options that the SEC could give you was using KMnO4, or we could use the KiO3, the potassium iodate, to liberate our iodine from. We're now using bleach to do that. So in your homework I've given you the video link for you to watch if you so wish. But just to remind ourselves, the thiosulfate is going in our burette, and now down here we're going to have our diluted bleach, we're going to have some sulfuric acid, and we have the Ki in excess in here. So yeah, this is just repeating what we've already done. Now, on a really, really lucky day, you'll only get the titration equation perfect. On a day where they decide to make it a little bit more complicated, then they'll give you your flask equation, and you need to be prepared to be able to use both. So here it is 1 equivalent, iodine over here is 1 equivalent. I can leave this as 1 equivalent here, and it's going to give me 2 thiosulfates in terms of a ratio. Okay, so our ratio is 1:1:2. The indicator that we use, again, for the iodine thiosulfate is the exact same one. Iodine is self-indicating at the beginning, and the color changes are really important. So at the beginning we start off with the brown-red color. Toward the end point we're looking for a pale straw yellow. Once you add your starch, it's going to go blue-black in color, and at your end point it's going to go colorless. Now, again, if we were in lesson, these would be the steps we'd be doing. you will always have a dilution factor in the question, and you need to find it. So this, we would be taking 25 centimeters cubed, and we would be putting it up into 250 centimeters cubed, and that's the same. So 250 divided by 25 gives me 10, so it's a dilution factor of 10. We would then be pipetting our bleach accurately, so we know what it is. We would be using a graduated for our sulfuric because we just want that in our vessel, and we know that this is going to be in excess, but we're still going to measure the Ki out accurately, and then we perform our titration. So we would have collected our data, and again, you set up your table to show everything. Now, what I will say is, this is the way I'm setting up my the table in this instance, so it's slightly backwards from what we would, maybe you would usually do. And I'm also leaving the ions in here. But I go back and reiterate, when you have to be calculating molar masses of things, you are going to use the full formula, not the ionic formula. The ion, the sodium that's removed here, it's just a spectator ion. It isn't involved in the redox. It has the same oxidation state on the left side and the right side of the arrow, so it's not included. So here this would be NaClO, would be our formula for the hypochlorite. So please bear in mind, calculating molar mass, you need full formulas. They'll be written in bold, and away we go. So this is the question that I've asked you to do. So you need to set up your table for yourself and find your ratios. And the only thing that I will just say here is that this is exactly like the ethanoic acid titration. So we want big M NaClO diluted, so that's the W. We then want big M NaClO original, so you're going to be using your dilution factor to find the original concentration. We are going to be looking at the grams per liter of our bleach in our original, and this last bit is the bit that is the poor relation. Everyone forgets it, but it's so important. So that is percent weight per volume of NaClO, and again that's in our original, and percent weight per volume means grams per 100 centimeters cubed. Okay, and I've written here wrong, haven't I? It should be grams per liter. So this is just a conversion between these last two bullet points. So pause, give the maths a go, and then when you're ready, keep going. So this is what our table will look like. So this is the information that you should have written in. And it goes without saying that this is going to be our way in. The extra information from the question is the dilution. So it's going to give us a dilution factor of 10. And we hit our maths the way we've always hit our maths. So the 0.12 moles is equivalent to 0.12 moles per 1,000. We convert that to 1 centimeter cubed by dividing 0.12 by 1,000. We then figure out what is the moles of thiosulfate at our endpoint. So we multiply moles per centimeter cubed by the titer volume. So that gives us down here. We then use our ratio, and the ratio that we're interested specifically here is we're going all the way from thiosulfate to ClO minus. If they ask for iodine, you will be able to work that out. So the equivalent of a ratio of 2:1 means I have 0.001926 moles in 25 centimeter cubed. I convert that, the 0.001926 moles, into moles per centimeter cubed by dividing it by 25, and I convert it to moles per liter by multiplying it by 1,000. So I now have, this is big M, and this is my diluted bleach. So we've already done our calculation that gives us our dilution factor of 10, and we multiply our diluted bleach by 10, and that's now giving us our concentration of the original bleach or undiluted bleach, so 0.77 molar NaClO. We then have to work out my concentration in grams per liter. So that is NaClO, so 16, 35.5, 23. So chlorine is always going to be 35.5. When we do that piece of maths, it gives us 74.5. So I multiply by moles of undiluted bleach, original bleach, by the molar mass of NaClO. It gives me 57.4 grams per liter. My last question is asking me to convert it to percent weight per volume. So I have grams per 1000 centimeter cubed here. And to go from 1000 to 100, if you want to go about it the long way, there's no problem doing that. You divide it by 1000 to find out what's in 1, and you multiply it by 100 to find out what's in 100. So that's going to give you 5.74 grams per 100, and you just need to write it with the units percent weight per volume. Okay, and that is us.